Hi, in this video we discuss what design of experiments, or short DOE, is, what the process steps of a DOE project are, how a DOE can help you reduce the number of experiments, how to estimate the number of experiments needed, and we go through the most common types of design. Finally, I'll show you how to create a DOE online with DataTab. Let's start with the first question. What is design of experiments? Design of experiments is a systematic approach to planning, conducting, and analyzing experiments. But what is the aim of design of experiments? The aim is to analyze the relationship between several input variables and an output variable. The input variables of the system are called factors, and the output variable is called response variable. Of course, there can also be several response variables. Therefore, factors are the variables believed to affect the response. Each factor now has at least two levels. These levels are the specific values a factor can take. And we want to find out whether a change in the levels of the factors has an influence on the response. Let's look at an example. When you pedal a bike, the wheels rotate around a central rod known as the axle. To ensure that the wheel can spin, there are bearings. Now imagine you're pedaling your bike on a smooth road. If the bearings are in good condition, the wheels will spin easily. The so-called frictional torque in this case is low. If the bearing is in not a good condition, you have to push harder to keep the same speed because there's more frictional torque. Now we want to investigate what influences the frictional torque of a bearing using a DOE. In this case, frictional torque is obviously our response variable. Possible factors could be lubrication or temperature. Lubrication could have the levels oiled and greased, and temperature could have the levels low, medium, and high. Now we want to know what influence the different levels have on the response variable. DOE is now helping us to create an efficient test plan to determine this influence. Especially if we have not only two variables but several, this can result in great savings. For sure, depending on the field of study, the system under investigation can be a process, a machine, or a product. But of course also humans, for example if you want to investigate the influence of medication. But what are the two main areas of application of design of experiments? Either you want to identify relevant factors, i.e., you want to know which factors have a significant influence on the response variable, or you want to find the optimal input variable. In other words, you want to find the input variables that optimize the response variable. Of course, both steps can also be carried out one after the other. So let's take a look at the process of a DOE project: planning, screening, optimization, and verification. In the first step, planning, three things are important. First, to gain clear understanding of the problem and the system. Second, to determine one or more response variables. Third, identify factors that can significantly influence the response variable. The task of determining potential factors that influence the response variable can be very complex and time-consuming. For example, a fishbone diagram can be created in a team. Now comes the second step, the screening. If there are many factors that could have an influence, usually more than 4 to 6 factors, screening experiments should be carried out to reduce the number of factors. Why is this important? The number of factors to be investigated has a major influence on the number of experiments required. Note, in design of experiments, the individual experiments are also simply called runs. In the full factorial design, which we will discuss in more detail in a moment, the number of experiments or runs is n equal to 2 to the power of k, where n is the number of runs and k is the number of factors. Here is a small overview. If we have 3 factors, for example, we have to make at least 8 runs. With 7 factors, it is already at least 128 runs, and with 10 factors, it is already at least 1024 runs. Please note that this table applies to a DOE where each factor only has 2 levels. Otherwise, there will be even more runs. Depending on how complex an individual experiment is, it may therefore be worthwhile to select so-called screening designs for 4 or more factors. Later, we will discuss the fractional factorial design and the Plackett-Burman design, which can be used for screening experiments. Once the significant factors have been identified using screening designs, and hopefully the number of factors has been reduced, further experiments can now be conducted. The data obtained can then be used to create a regression model, which helps to determine the input variables in such a way that the response variable is optimized. After optimization comes the final step, verification. This involves checking once again whether the calculated optimal input variables really have the desired influence on the response variable. Depending on whether we are in the screening step or the optimization step, there are different types of design. The best known are full factorial design, fractional factorial design, Plackett-Burman design, Box-Behnken design, central composite design. Of course, you can create all these types of designs online at datatab.net. Let's first take a look at the full factorial and the fractional factorial design. We can then also answer the question, why all the effort? Why design of experiments, and what do we need statistics for? Experiments cost time and money. The number of runs should therefore be kept as small as possible. But beware, if the number of runs is too small, there is a high risk that relevant differences will not be recognized. Let's take a look at an example. We would like to investigate which factors have an influence on the frictional torque of a bearing. Let's start with one factor, lubrication. We would like to know whether it has an influence on the frictional torque if a bearing is oiled or greased. To find out, we take a random sample of 10 bearings. We oil one half of the bearings and grease the other half. Now we can measure the frictional torque of the 5 oiled bearings and the 5 greased bearings. But stop, why 10 bearings? In most cases, each run costs a lot of money. Perhaps we can manage with fewer runs. So how many experiments do we need in order to find out if the lubricant has an effect on the frictional torque? Let's just start with the 10 bearings. We can now calculate the mean value of the frictional torque of the oiled and greased bearings. Then we can calculate the difference between the two mean values. In this sample, we can see that there is a difference between oiled and greased. However, we can already see that the frictional torque in the oiled and greased bearings is highly scattered. If we take another random sample of 10 bearings, it is possible that this time the difference will be greater, but it is also possible that the difference will be in exactly the opposite direction. In other words, the frictional torque of the bearing scatters. The wider the spread, the more difficult it is to identify a specific difference or effect. Fortunately, the variability of the mean value can be reduced by increasing the sample size. The larger the sample size, the more precise is the estimation of the mean. Therefore, the smaller the effect and the wider the spread of the response variable, the larger the sample needs to be. But how much larger? How can you estimate the number of runs needed? You can use this formula as an approximation. Here, n is the number of runs, sigma is the standard deviation, and delta is the effect to be determined. For example, if we have a standard deviation of 3 Nm and a difference of 5 Nm is relevant for us, then we need 22 runs. If we only have a standard deviation of 2 Nm, we only need 10 runs, and with a standard deviation of 1 Nm, we get 2.4. So we need 2 runs with greased bearings and 2 runs with oiled bearings. But how can DoE help you reduce the number of runs? Let's assume that the calculation of the number of runs results in 16 experiments. So 8 runs with oiled bearings and 8 runs with greased bearings. But what if we have a second factor? Let's say in addition to lubrication we have temperature with low and high. Then we need another 8 runs to take these factors into account. So we need 16 runs to check if the lubricant has an effect and 16 runs to check if the temperature has an effect. This gives us a total of 24 runs. Now the question arises, is it possible to achieve this with fewer runs? And that brings us to the full factorial design. The question is, why should we limit ourselves to testing one factor at a time? Instead, we could devise a design that incorporates the fourth potential combination, which is grease and high temperature. Of course, we still need 16 runs per factor. We get this by making 4 runs with each of the 4 combinations. Then we have 8 runs with oil and 8 with grease. And on the other side, 8 with low temperature and 8 with high temperature. We now have a total of 16 runs. Before that, we had 24 runs. We now need fewer experiments and get even more information. Why more information? We now also know whether there is an interaction between temperature and lubrication. For example, oiled bearings may show a variation in frictional torque at different temperatures, which is not observed with greased bearings. This information would have been lost previously. Now, when we have 3 factors instead of 2, the savings are even higher. If we test one of the 3 factors at a time, we need 32 runs. If we now run 2 experiments for each combination in a full factorial design, we still only need 16 runs. However, for each factor, we still have 8 runs per factor level. For example, for the lubrication factor, we have 8 runs with oil and 8 runs with grease. Of course, we can also create full factorial designs with more than 2 levels. For example, the temperature factor could have 3 factor levels: low, medium and high. However, as mentioned at the beginning, even with a full factorial design with 2 levels in each factor, the number of runs required increases very quickly as the number of factors increases. Let us therefore now take a look at the fractional factorial design. The fractional factorial design is used for screening designs, i.e. if you have more than approximately 4 to 6 factors. Of course, reducing the number of runs means reducing information. In fractional factorial designs, the resolution is reduced. What is the resolution? The resolution is a measure of how well a DoE can distinguish between different effects. More precisely, the resolution indicates how much the main effects and interaction effects are confounded in a design. But what are main effects and interaction effects? And what does confounded mean? In design of experiments, the term effect refers to the impact that a certain factor or a combination of factors has on the response variable of an experiment. Essentially, they measure how much the response variable changes when you change the factors. A main effect is now the influence of a single factor on the response variable. For example, what influence the lubrication of a bearing has on the frictional torque. Interaction effects occur when the effect of one factor on the response variable depends on the level of another factor. For example, the effect of the lubricant on the frictional torque could depend on the temperature. But what does that mean? Let's say we have an average frictional torque value of 102 Nm for the bearings with oil and an average value of 108 Nm for the bearings with grease. Then we have a main effective lubrication of 6 Nm. But now we can break this down into high and low temperatures. At high temperature, we could get 98 for oil and 102 for grease, so the difference between oil and grease is only 4 Nm. At low temperature, we could get 104 and 112, so a difference of 8. So the lubrication factor is influenced by the temperature, and we have an interaction between lubrication and temperature. The interaction leads to a difference of 2 Nm to the original result. We therefore have an interaction effect of 2 Nm. Full factorial designs take all interactions into account. In our bearing friction example, in addition to the lubricant and temperature factors, we also looked at the interaction between lubricant and temperature. However, as the number of factors increases, numerous interactions rapidly emerge. For example, if we have the 5 factors A, B, C, D and E, We get the interaction between 2 factors, between 3 factors, between 4 factors, and between all 5 factors. Now, of course, the question is, do we really need all the interactions or can we reduce the resolution? And this is exactly what the fractional factorial design does. In a fractional factorial design, interactions can be confounded with other interactions or with main effects of factors. What does confounded mean? Effects of different factors or the effect of interaction of factors cannot be separated from each other. The extent to which the number of runs can be reduced at the expense of resolution is shown in this table. The resolution is usually indicated by Roman numerals, e.g. 3, 4, 5, and so on and so forth. Here on the diagonal, we see the full factorial designs. We'll go through what resolutions 3, 4, and 5 mean in a moment. For example, if we have 6 factors, we need at least 64 runs for a full factorial design. If we choose a fractional factorial design with a resolution of 6, we need 32 runs. With a resolution of 4, we need 16 runs. And with a resolution of 3, we need only 8 runs. But what does that mean and how does it work? The full factorial design is always used as the starting point. Let's take a look at the example with 8 runs. Let's say we have the factors a, b, and c. With the full factorial design, we can now test whether factor a, b, or c have an effect. We can test whether the interactions with 2 factors have an effect and whether the interaction with all 3 factors has an effect. If we now want to test not just 3 factors with 8 runs but an additional 4th factor, say factor d, then we must drop the information from one of the interactions, for example the interaction of a, b, and c. If we want to test a 5th factor with 8 trials, let's say factor e, then we will have to drop another interaction, for example the interaction between b and c. But I didn't express myself correctly. We are not actually dropping the information. We are mixing the new factor with the interaction. We've confounded the factor with the interaction. What does that mean? It means that we are unable to determine if an observed effect is attributable to factor d or to the interaction of a, b, and c. Similarly, we can't distinguish if an effect results from factor e or from the interaction of a and b. Of course, it is much less critical to mix one factor with an interaction of 3 factors than with an interaction of 2 factors. And now we have a good transition to the resolution. What do the resolutions 3, 4, and 5 mean? At resolution 3, main effects can be confounded with interactions of 2 factors. For example, factor d with the interaction of the factors a and b. Experiments with resolution 3 should therefore be considered as critical. They can only be used if the interaction of 2 factors is significantly smaller than the effects of the main factors. Otherwise, the interaction of 2 factors can significantly distort the result of 1 factor. Experiments at resolution 4 are much less critical. Here, only the main effects are confounded with the interactions of the 3 factors. And the more factors are involved in an interaction, the smaller the effect is likely to be. Furthermore, in resolution 4, interactions with 2 factors are confounded with interactions with other 2 factors. Experiments at resolution 5 are not considered critical. Main effects are only confounded with interactions of 4 factors. In the same way, 2-factor interactions are only confounded with interactions of 3 factors. But how do you confound a factor and an interaction? Let's take a look at this example. Here we have the full factorial design of the 3 factors a, b, and c. These 8 runs are carried out in total. We still only consider factors with 2 levels. -1 stands for one level and 1 for the other. For our frictional torque example, the test plan would then look like this. For example, for the factor temperature, -1 is the low temperature and 1 is the high temperature. If we now run the experiments, we obtain a value for the response variable for each run. If the factor A is 1 or -1, This has a certain effect on the target value, exactly the same if the factor b is 1 or minus 1. The interaction effect now tells us whether there is an additional effect if factor a and b are simultaneously 1 or minus 1, or if both go in exactly the opposite direction. So on one side we have the pairings with the same sign, and on the other side the pairings with an unequal sign. Now we can check whether there is a difference in the response variable between the values in the green group and the values in the red group. If yes, then there is an interaction between A and B. However, if we know in advance that there is only a very small interaction, if any, then we can use these combinations to test a fourth factor D. To do this, we simply multiply A and B. Now we always have a 1 if the factors A and B have the same sign and minus 1 if they have a different sign. Now, of course, a problem may arise when analyzing the results. If there is a difference between the green and the red values in the response variable, we cannot say whether this effect comes from the interaction between A and B or whether the effect comes from the factor D. If we are already sure that there can be no interaction between A and B, this is of course not a problem. Then we can be sure that the difference is due to factor D. In the same way, we can now take the interaction of A and C and also measure factor E, and the interaction of A and B and C and measure factor F. Therefore, in this case, we measure 6 factors with only 8 runs, but we can no longer distinguish the factor D from the interaction A and B. We can no longer distinguish the factor E from the interaction A and C, and we can no longer distinguish factor F from the interaction A, B, and C. And now let's take a quick look at the other types of designs, and then I'll show you how you can create a DoE online with DataTab. Plackett-Burman designs. Plackett-Burman designs are usually designs with 2 levels and with resolution 3. The main advantage of Plackett-Burman designs is that the interaction of 2 factors is distributed over several factors. For example, the interaction AB is confounded with all factors except with the factors A and B. This makes Plackett-Burman designs particularly suitable when there are many factors and only the main effects are of interest. But beware, Plackett-Burman designs should only be used if it can be assumed that we can neglect 2-factor interactions. However, this requirement is not quite as strict as for classical fractional factorial designs of resolution 3. Let's move on to the last 2 designs. The central composite design and the Box-Behnken design aim to analyze and optimize a few factors in more detail and can identify nonlinear dependencies. To determine nonlinear dependencies, at least 3 levels per factor are required. With a full factorial design with 3 levels, however, the number of trials increases very quickly. With 2 factors with 3 levels each, we need 9 runs. With 3 factors with 3 levels each, we already need 27 runs. The number of attempts increases with 3 times the number of factors. This is where the Box-Behnken design comes into play. A full factorial design is created with 2 levels in each case. Further, the center point is included in the design, for example, 3 times. For example, with 2 factors, we have the full factorial design with 2 levels plus the center point, as well as with 3 factors. This greatly reduces the number of runs, in this case from 27 to 15. Nevertheless, nonlinear relationships can be determined. Let's move on to the last design, the central composite design. A central composite design typically consists of 3 different types of test points. 2-level full factorial points. These form the corner points of a cube or a hypercube in multidimensional spaces. Central points. They lie in the center of the space defined by the factorial points. Axial points. These lie on the axis of the factor space outside the cube. The last 2 points help to estimate the nonlinear effects. And now I'll show you how you can create your DoE online with DataTab. To do this, simply go to datatab.net, Click on plus and then on DoE. Here you can select which design type you would like to create, e.g. a full factorial design or a fractional factorial design. Next, you can select the number of factors and make specific settings for the respective designs. For the fractional factorial design, for example, you can specify the number of factors and the number of runs. You can now enter the names of the factors and the values for the levels. For example, temperature with low and high, and lubrication with oil and grease. Here you can see the experiments. Each row is one run or one experiment. Further, you can export the table to Excel. Now you can carry out the experiments. After you have performed the tests, you can copy all the data back to Data tab and evaluate the results. But more on that in the next video. I hope you enjoyed this video and I'll see you again soon.